All right, so get ready, because today we are diving headfirst into the fascinating world of scientific explanation. We've got a whole stack of articles and research lined up, and with your philosophical mind, I think you're really going to enjoy this one. We're going deep on some pretty big questions, like what actually makes a scientific explanation good? Sometimes, even if it's technically right, you're still left with that feeling of like something's missing.
Yeah, it's so true. It's funny how we just sort of accept explanations, especially in science, without really questioning them. You see something happen, you get an explanation, and you move on. But when you really stop and think about it, the whole thing gets surprisingly complex.
Oh, totally.
Like, can statistics really explain a single event? Or are they just telling us about probabilities?
Right.
And do we always need a chain of cause and effect to feel like we actually understand something?
It's like we're pulling on this one thread and it's unraveling this whole sweater of like assumptions about how we make sense of the world.
Hmm, perfect analogy.
So to start untangling this mess, let's go back to basics, like way back, to this model that's considered a classic in the philosophy of science, almost like the gold standard,
Hmm.
the deductive nomological model, or DN model for short.
Yes, the DN model.
So-
So influential and yet so debated.
Right.
It's all about logic, like a perfectly formed argument.
Okay, I'm listening.
You have the explanandum, which is basically the thing you're trying to explain.
So like, why do planets move in those elliptical orbits?
Exactly. And then you have the explanus, which is all the stuff that does the explaining.
Okay, so what goes into that?
Initial conditions, like where the planets started, how fast they were going, and super importantly, you need at least one general law of nature. In our planet's case, it would be Newton's law of gravity.
So it's like plugging numbers into a formula and getting a result that you can predict.
Ah.
But does it always work out so neatly in the real world?
That's where things start to get tricky. The DN model looks great on paper, nice and clean, but then you run into these weird real-world situations where it just doesn't quite fit.
Oh, like what?
Think about a flagpole and its shadow. Like classic example, right?
Yeah. Oh?
The DN model would say explaining the shadow's length from the height of the pole is just as good as explaining the pole's height from the shadow's length. But come on, we know intuitively that's just not right.
You're telling me the shadow somehow caused the flagpole to be that tall? It seems backwards.
Exactly. It's like the DN model is missing something about the direction of explanation, the whole cause and effect thing.
Yeah, and that's not the only problem, is it? I feel like I've heard critiques about it being too simplistic or something.
Oh, definitely. The DN model really struggles with irrelevancies. Imagine this law that says all ravens are black.
Okay.
Now imagine someone trying to be all scientific and saying this raven is black because it's a raven and all ravens are black. Technically, it fits the DN model, but it feels like we're just going in circles.
It's like saying water is wet because it's water. True, but not very helpful.
Exactly. It doesn't really explain anything new. Like there's this deeper level of understanding that the DN model just doesn't get at.
So the DN model might need a little more work, especially when it comes to cause and effect. But what about a model that's all about probabilities and statistics? I'm thinking of the statistical relevance model or the SR model. Does that one do any better?
The SR model definitely offers a fresh perspective. It's all about finding the factors that statistically matter to an outcome. We don't necessarily need a direct step-by-step causal chain.
Give me an example.
Think about taking birth control pills. That's statistically irrelevant to male pregnancy, but very relevant to female pregnancy.
Okay, I see. So instead of demanding a perfect logical deduction,
Yeah.
the SR model saying, let's find the things that actually make a difference, statistically speaking.
Right.
But does that mean we reduce everything to just probabilities? What about those 1 in a million events that seem to defy all the odds? Can the SR model handle that?
That's one of the coolest things about the SR model. It's surprisingly good at explaining those really rare events.
Right. Really?
Think of winning the lottery. It's crazy unlikely, right? But if you've got the winning ticket, we can explain your win by pointing to that one crucial factor.
So it's not just about how likely an event is, but about finding the specific thing that made it happen, even if the odds were stacked against it.
Exactly.
That is pretty cool. It almost changes our whole idea of what a good explanation is.
For sure. And this is why the SR model has been so important, especially in fields that deal with a lot of complexity and probability, like epidemiology or climate science.
But I'm guessing it doesn't solve all our problems, right? Like, philosophically speaking, there are still some big questions, especially when it comes to individual events and the nature of cause and effect.
Oh, absolutely.
Like, can we truly explain a single event just by pointing to statistical correlations.
Right.
Isn't there something more to understanding why something happened beyond just knowing the factors that made it statistically more likely?
That is the million-dollar question. Some argue that statistical models are great for explaining patterns and trends, but they just don't cut it when we're dealing with individual events.
Especially in areas like quantum mechanics where things get really weird.
Yeah, for sure.
It's one thing to explain why a certain percentage of atoms decay over time, but it's a whole other thing to explain why this particular atom decayed at this precise moment.
Yeah.
I'm sensing we're wading into some pretty deep philosophical waters here.
Oh, absolutely. We are just getting started. It's like we're always trying to find that balance between what we can predict and what's just totally random.
Yeah.
But okay, so the DN model is about that abstract logic, and the SR model is diving into probabilities. But is there a model that really gets into the nuts and bolts of how things happen in the real world? Cause and effect, the actual mechanisms, all of that.
You're totally reading my mind, because that leads us perfectly to our next model, the causal mechanical model, or CM model. So the DM model is like a logical blueprint, and the SR model is like a statistical map. The CM model wants to show us the actual machinery, like pop the hood and see how it works.
Exactly. Think of it as this chain reaction, like one event triggering the next in a continuous process. A good explanation, according to the CM model, is all about tracing those processes and seeing how they transmit that causal influence. Kind of like watching dominoes fall in slow motion, seeing each domino knock over the next.
So instead of just saying A caused B, the CM model wants to show us how A caused B step by step.
Yeah.
So not just that the cue ball hit the 8 ball, but the angle, the transfer of momentum, like a whole physics replay.
Precisely. It's about uncovering those physical mechanisms that make things happen. And the classic example, of course, is billiard balls. We can trace where each ball goes, see how they interact during the collision, and even factor in things like friction and spin. It's all right there in front of us.
It's like zooming in on a microscopic level and seeing cause and effect unfold in real time. But does this model work for everything? Like, does it only work for those simple physical interactions, like our billiard balls? What about when we try to explain something like gravity? Or what about a gas, with billions of molecules? Can we use the CM model for that?
Well, that's where the CM model starts to hit some roadblocks. It's great for those straightforward interactions where things are physically touching, but when we get to action at a distance, like with gravity, it gets a bit more complicated. We can describe the force, sure, but how do you actually trace a continuous process when the objects aren't physically connected?
Yeah, it's like trying to explain how the Earth is pulled towards the sun without any visible strings attached. What about those complex systems you mentioned? Like, if we tried to explain how a gas behaves using the CM model, would we have to track the movement of every single molecule? That sounds like a computational nightmare.
You nailed it. The CM model's focus on these continuous processes can become a bit overwhelming, especially with those systems that have tons of interacting parts. It's just not practical or even possible to track every single interaction.
So it's like trying to understand a traffic jam by looking at each car individually. You get bogged down in the details and miss the bigger picture of why the traffic is jammed in the first place.
Exactly. For those complex systems, we need ways to describe what's happening at a higher level without getting lost in the microscopic details. Instead of tracking each molecule in a gas, we can talk about temperature, pressure, and volume, those factors that influence the overall behavior of the gas.
So it's like shifting our focus from individual trees to the whole forest, right? We're looking for those big picture variables that describe the system's overall behavior, even if we can't trace every single interaction happening at the micro level.
Right. And it highlights an important point. A good explanation needs that right level of detail. Too much detail, and it's overwhelming. Too little detail, and you miss crucial information. It's all about finding that sweet spot where you capture the essence of the phenomenon without getting lost in the weeds.
It's like choosing the right lens for your camera, right?
Yeah.
You need that right magnification to capture the subject, whether it's a tiny insect or a vast landscape. But even if we could track every molecule in a gas, wouldn't we still be missing something important?
Absolutely. Even if we had a perfect record of every molecular trajectory, it still wouldn't tell us why the gas behaves the way it does in general. It wouldn't explain why so many other possible configurations of those molecules could lead to the same outcome on a larger scale.
It's not just about what did happen, but also about what could have happened,
Yeah.
right? We need a model that can deal with those possibilities, those underlying patterns that shape the behavior of the system.
That's a great point. It's not enough to look at isolated events. We need to understand the underlying principles, the possibilities. And that brings us to a model that emphasizes the power of unification, finding those deep connections that reveal a hidden order in the universe.
Unification. It sounds almost mystical, like we're searching for the secret code that unlocks the mysteries of the cosmos.
While there's certainly a sense of wonder and awe involved in this model, it's called the unificationist model of scientific explanation, and it really celebrates those aha moments when we realize that seemingly unrelated things are actually connected by some deeper principle.
Okay, hit me with that aha moment. Tell me about this model. What makes it different?
The unificationist model says the best explanations are the ones that connect the most diverse phenomena using the fewest and most stringent principles. The more we can explain with a small set of powerful ideas, the better our understanding.
So it's like finding that ultimate theory of everything, the one equation to rule them all.
You're getting it. Think of Newton's law of universal gravitation. It explains why apples fall from trees and why planets orbit the sun. It unifies those two seemingly separate things under one elegant principle.
It's like finding that hidden thread that connects all the beads on a necklace. Suddenly, everything clicks into place. But I'm curious, can this model deal with cause and effect? Does it just explain what happens, or can it tell us why it happened in that specific way?
That's a great question, and one that philosophers have been debating for a while. Some argue that the unificationist model is really good at showing how things are connected, but it struggles to capture those directional, asymmetrical aspects of causation that we talked about earlier.
So, like, it can explain why apples and planets are both drawn to large objects, but it wouldn't necessarily explain why the apple falls to the earth and not the other way around.
You got it. The unificationist model, in its purest form, might say that explaining the past with the future is just as valid as explaining the future with the past, even though that doesn't feel quite right to us.
It's like saying that knowing where the billiard balls end up is just as explanatory as knowing where they started. It just feels like we're missing that sense of time moving forward, that directionality of cause and effect.
You're highlighting a tension at the heart of the unificationist model. On the one hand, it's incredibly powerful to find those unifying principles that connect seemingly different things. But on the other hand, it might not always capture those nuances of causation that we just inherently understand.
It feels like we're still on the hunt for that perfect model, the one that can handle the elegance of unification and the messiness of cause and effect all in one. So where do we go from here? It's amazing how we started with logic and deductions and then moved to probabilities and mechanisms, and now we're talking about these big unifying principles. It feels like we've scaled this mountain of explanation, but there's still one peak left. What about that human element you mentioned before? The idea that an explanation isn't just about the facts, it's also about who's giving the explanation and who's listening.
You're taking us right to our final model, the pragmatic theory of explanation. And this one shifts our focus. Instead of trying to find some objective definition of a good explanation that applies in every situation, it recognizes that explanation is an act of communication, a conversation between the person doing the explaining and their audience.
So instead of looking for the one right explanation, it's more about finding the explanation that works best for a particular person at a particular time.
Exactly. Pragmatic theories say that whether or not an explanation is successful depends on things like what the audience already knows, what they're interested in, and even the specific question they're asking.
That makes a lot of sense. An explanation that might, wow, a physicist could leave me totally lost, and something that seems super insightful to me might bore a historian. Right? It's like we're speaking different languages. Can you give me an example of how this plays out in real life?
Let's go back to our flagpole and its shadow. Remember how other models struggle to explain the height of the flagpole based on the length of the shadow, even though you could technically make a deduction?
Yeah, it felt like we were getting cause and effect mixed up. How did these pragmatic theories handle that?
They say that explanations are answers to questions and that the context of those questions is really important. In one context, we might be asking how shadows are formed. In that case, explaining the shadow's length from the height of the pole makes total sense. But in another context, we might be asking about why the flagpole was designed the way it was.
Oh, I get it. So if we're asking why the flagpole was built to a certain height, it suddenly makes sense to explain that height in terms of the shadow it casts. Like maybe they wanted the shadow to fall in a certain spot at a certain time of day.
Exactly. The pragmatic theory says both of those explanations can be right, depending on what the audience is trying to understand. It's not about finding a universally true explanation. It's about giving information that's relevant and useful in a specific situation.
So it's like choosing the right tool for the job. A hammer is great for nails, but not so great for screws. And different models of explanation might be better suited for different situations. But doesn't this make things a bit too subjective? Does it mean anything goes as long as the audience buys it?
That's a concern a lot of people have, but pragmatic theories aren't saying that any explanation is as good as any other. We still need standards for truth, accuracy, and relevance, but those standards change depending on the context.
So it's not that anything goes, it's more like different things go in different situations. So a simplified explanation might be great for a kid learning about something for the first time, while a more detailed one would be better for experts.
Exactly. And this brings us back to something we've been talking about this whole time: how complex explanations really are. There might not be one right answer, one model that works for everything. Each model gives us valuable insights into what makes a good explanation, but the best model often depends on what you're trying to explain and in what situation.
This has been such a fascinating journey. We went from the strict logic of the DN model to the statistical world of the SR model, from the inner workings of the CM model to the unifying power of the unificationist model, and we ended up with this pragmatic approach that puts humans at the center of it all. It feels like we've explored this whole map of different ways to understand why things are the way they are.
And that map, just like a real map, shows us where we are and all the paths we could take. There's so much more to discover, so much more to explore.
Speaking of exploring, I'm left with one question that just won't go away. We've seen how all these models highlight different parts of a good explanation, but how do we choose which model to use in a given situation? Is it the same for a physicist as it is for a biologist or a sociologist? If scientific explanation is about finding the most relevant causes, how do we decide what's relevant in different fields?
That's a question we're thinking about, and it takes us right to the edge of this deep dive. It reminds us that the way we understand explanations is constantly evolving, and there's always something new to discover, something new to question, something new to learn.
And that's what makes it so exciting. Thanks for joining us on this intellectual adventure. We went deep on some pretty heady stuff, and hopefully we've all come away with a new appreciation for how complex and fascinating scientific explanation can be. Until next time, keep asking those why questions, keep digging deeper, and keep searching for those satisfying aha moments.